How's everybody doing? Yeah. You ready for the quiz? Yeah. You find out, huh?
Yeah. Are we allowed to use the PowerPoint for the quiz?
Sure. You can use whatever you want.
One thing I'm kind of iffy about is would the quiz work on the iPad or would I just have to go to the computer to like in the library?
Are you able to get into Canvas on
Yeah,
that?
there's the Canvas app and I'm able to get it on it.
You should be fine then.
Okay. With parks.
So I don't know why the projector is not working. For those of you who are dialed in, can you see my screen?
Yeah, we can. Or at least I can.
Can the people who are dialed in see my screen?
Yes.
Yeah, I can,
You hear
I
me?
just don't know if you,
Anybody?
yeah, we can see it.
I don't think you can hear us.
You know what happened there?
Can you hear us?
Yeah, can you hear me?
Yeah, could you hear us earlier?
No, we could not.
Okay, we were all talking to you earlier.
Okay. Yeah, I couldn't hear you. I guess you couldn't hear me because I was asking you guys questions.
Oh, we could hear you. We were responding. You just couldn't hear us, I think.
Oh, okay. All right. Well, I have no idea what was going on there, but can you see my screen now?
Yeah, we can. We could in the beginning.
Oh, you could?
Yeah.
Okay, because we couldn't see it here in the room. All right, thank you. Well, that was fun. Now, why is it showing that? Huh. Oh. So those of you who are online, are you seeing just the slide, or are you seeing the slide and little slides on the bottom?
Just the slide.
Okay. All right. Well, I apologize for the people who are here. We're just going to go with this so we can get going. My streak of no technical difficulties has officially ended with this class. All right. Sorry about that. Sorry about the delay. What we're going to do today is we're going to pick up on chapter 2 where we left off and go through a portion of that. About halfway through the class, we're going to stop, and then you'll log into Canvas, and then you'll start your quiz. The way the quiz works is that once you log into Canvas and pull the quiz up, it starts a timer on the quiz. So the quiz is 15 questions, and the quiz time is 15 minutes. So I would just say, don't be intimidated by 15 questions in 15 minutes. Some of the questions, it's literally going to take you 10 seconds to answer. Some of the questions, it's going to take you a few minutes to answer. So it should all even out, but don't get hung up on that. Just start working, answer the questions best you can, and go through. They're all multiple choice. And don't start the quiz until you're ready to get started, okay? Don't be in a rush to start it. Get all set up, get any notes or anything that you're using ready and all that before you start. Any questions about the quiz?
Can I ask a question about the material?
Sure.
Okay, so like when we're doing the conversions or whatever, you get the number, but how do you know when you need to put it in sig figs? Like, how do you know when you need to put it in the scientific notation?
So the significant figures are going to be based on the data that you're using to do the calculation. So say, for instance, you know, you're doing like something where you're multiplying a weight times the density. Then you would want to arrange it so you have the units canceling correctly. So that would tell you, do you leave the density as grams per mil, or do you flip it over and have the mils in the numerator, the grams in the denominator? But each of those numbers is a measurement. And so the significant figures in those measurements drive how many significant figures should be in your answer. In other words, if you had a weight that had 4 significant figures and you had a density that had 3 significant figures, then that 3 significant figure density would drive you to have 3 digits in your answer, 3 significant figures in your answer. Whether you would use scientific notation or not, that just depends on how you want to write it. For big numbers, we talked about how scientific notation is pretty useful to get the significant figures there, so you're not dealing with a lot of trailing zeros and things like that, or zeros in the beginning, which are not significant. So that's kind of a judgment call on you of the best way to express that.
So either way is okay?
Either way is okay. So in this exam, of course, since it's multiple choice, you'll see what your choices are.
Right.
And so, you know, you'll have to pick the one that's is the choice, obviously. Even though you can have equivalent answers, only one of them is going to be there.
Yeah, we were just confused because like in the homework, it said like, we would write our answers or whatever, and then we would check them in the back of the book and it would have the other option. And then we would revert to that option for the next one, and then it would have the other version. So I just wasn't sure if we needed to go with what the book was saying or if it didn't matter.
No, I mean, with some of that stuff, you can do it either way. So neither one is incorrect. But with this quiz, if there is anything like that, you know, you're going to have the choices to choose from. And so you'll have to pick the one that is appropriate.
Okay, thank you.
Mm-hmm. Anything else? Okay, let's talk about the periodic table a little bit more. So in the periodic table, there are groups. So the groups are the columns, if you recall. And some of the groups have common names that they're known as. So 1A is alkali metals. That's lithium, sodium, potassium on down the line. And 2 is alkaline earth metals. 6A is halogens. 7A is halogens, and 8A is noble gases. I'll be honest with you, the 6A one, I don't think I've ever called it that in my life, except for this class. The 1A, 2A, alkali metals and alkaline earth metals, that's fairly common that people refer to those. Halogens is real common in 7A, and noble gases, that's pretty standard as well. So we'll talk about this a little bit more. So when we look at the periodic table, and we've got one down here in the lower right-hand side, the elements in the upper right, kind of in the light green, those are the nonmetals. Or the ones all to the left, the kind of light yellow, those are the metals. And then the ones that go along that stair step, which are kind of like a purplish color, those are the metalloids. So let's talk a little bit about the metals first. So we see there's a lot of metals. That's the biggest category that we have. And those are grouped together because they have some similar properties. They're often shiny, and you see some of the example metals down at the bottom there. Those are all things that we're probably familiar with. And we're familiar with them. They're usually kind of shiny a little bit. They're usually solids. One exception to that is mercury. If you've seen mercury, it's a really dense liquid, but it is a liquid. But for the most part, metals are solids. One of the big things that metals give us are they can conduct heat and they can conduct electricity. So you think about things like copper wires and things like that you use for electrical wiring in your house. That's used because it can conduct the electricity. So as I mentioned, the nonmetals are in that upper right-hand corner, the kind of light green ones. The one thing I will note is that hydrogen, which is over in 1A, that is a nonmetal, so that's kind of the exception to the rule. The nonmetals can be solids, they can be liquids, they can be gases at room temperature. It's kind of a mix of things. The nonmetals are the ones that we tend to use for chemical reactions. elements. Those are the ones that are most likely to be involved in chemical reactions. As I mentioned, that kind of dark line is a stair-step thing over towards the right and has the purplish elements next to it. That line is the kind of the delineator between the metals and non-metals. And some of the elements that lie along that, so boron, silicon, and some others, those are considered metalloids. So that just means that some of their properties are more metal-like, some of their properties are more non-metal-like. Let's talk a moment about chemical formulas. When we write a chemical formula, we write the atom, and remember, that's either a single capital letter or it's a capital letter with a small letter next to it. And then we usually have a number next to that. And that number tells us how many of those atoms are in that molecule. Note that if it is 1, we don't write the 1. The 1 is just implied. But if it's some number other than 1, then we write that. And we see some examples here. We have hydrogen as H2, oxygen O2. Going down to the bottom, we have methane, CH4, ethylene, C2H4. So what that tells us is if we found a methane molecule somewhere, it would have 1 carbon and 4 hydrogens. Didn't matter where we found it. If it was really methane, it would have that formula. If we have 2 atoms together and they're the same atom, we call that a diatomic molecule. And so some of the elements occur naturally as diatomic molecules. And this is a list of them. Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. So in other words, you won't find hydrogen floating around by itself. You'll find H2. Same with nitrogen and oxygen and the others. So when we have this type of situation where it's 2 atoms of the same element, and this is how it naturally occurs, we call it diatomic. Because remember, diatomic would mean 2. When we express what the molecule looks like, or how we're naming it, or the composition, we have 2 types of formulas. We have empirical formulas and molecular formulas. Molecular formula tells us exactly how many of each of those atoms is in the molecule. Empirical formula is the lowest whole number ratio. So in other words, we can figure out an empirical formula from a molecular formula, but not vice versa. So if I give you the empirical formula of a compound and say, what's the molecular formula? You should tell me I need more information. I can't figure that out. If I give you a molecular formula and say, tell me what the empirical formula is, you should be able to do that. And we'll have an example here in a moment. So let's look at glucose. So the glucose molecular formula is C6H12O6. So that tells us in glucose, we have 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms. From this molecular formula information, we don't know exactly how they're arranged, but we know that's what's in there. So any glucose molecule we find, wherever it is, it'll have this combination of atoms. So anyone have a thought on what the empirical formula of this would be? You divide by 6, right. So if we divide by 6, because 6 will factor into each of those 3 subscript numbers, we'd have C, H2, and O. So once again, we don't write the 1s, because we said if it's 1, that's implied. So here we have the empirical formula for glucose along with the molecular formula. So if I asked you, here's the molecular formula, what's the empirical formula, you could do that simple mathematical operation and tell me the empirical. If I just wrote down CH2O and said what molecule this is, based on that empirical formula, that's not enough information for you. CH2O would be a different molecule than glucose. Caffeine, C8H10N4O2. How about that one? What would be the empirical formula of that? What could we divide all those by? You divide them all by 2. So then we'd have C4H5N2 and then oxygen. So sometimes we express things by their molecular formula, sometimes by their empirical formula. General rule of thumb is the inorganic compounds tend to be expressed by their empirical formula, and the carbon containing, the organic chemistry type compounds tend to be expressed by their molecular formula. The nice thing about the molecular formula is that we can use that information to get a molecular weight of the compound, which is useful in figuring out moles and things like that. So there's different ways that we can draw molecules in chemistry, and each way has a little bit different purpose to it. So if we look at these examples, these 5 examples, we see on the left is the molecular formula. And this is for, all of these are for methane. So we just talked about the molecular formula tells us how many atoms, which atoms and how many atoms are in a molecule. So in this case, methane, 1 carbon, 4 hydrogens. But that really doesn't tell us how those atoms are bonded together. It just tells us how many are there and which ones are there. The structural formula, the next one, where we see the 4 hydrogens bonded to the carbon, so the little straight lines represent a bond, tells us that that's the structure of methane. So that's the bonding. The problem with that one is that's just a one-dimensional drawing. And the molecules we know are 3-dimensional. So now we get to the perspective drawing, the next one over, and we're starting to introduce some of that stereochemistry, that dimensional nature of the molecules. When these perspective drawings, if you look at the triangle that's all colored in dark, that is considered to be, think of it as it's sticking out of the page coming at you. The triangle bond that you see with the dashed lines, the idea of that is that represents the bond going back into the page, so to speak. So what that does is starts to give us a little bit of feel for the 3-dimensionality of the molecule. The ball and stick model, the next one, it's a little easier to see that there is some dimensionality to it. It used to be people, when they took chemistry classes, would buy these little molecule kits where you'd literally have these little balls and sticks, and you'd assemble the molecules, and you could really see how the molecules kind of fit together. You don't see that much anymore. Everyone just does it on the computer. But that's what's going on in that ball and stick model. And then the final one, space filling model. Once again, these are all methane. There you start to see, remember we talked about how the nucleus is a tiny bit and there's an electron cloud around it, and different atoms have different sizes and just all that kind of stuff. We're starting to get a feel for that there. You have the carbon in the middle and its big electron cloud, then you have the smaller hydrogen molecules bonding to the sides, and then their electron cloud. So you get a feel for, a little more feel for that 3D nature of the molecules. A little later this semester, towards the end of the semester, we'll actually use some computer programs where you can see these types of space filling models, and you can rotate the molecule around to kind of get a feel for how it looks from different angles and get a little better feel for that spatial part of the molecule. So each of these has an appropriate time and place to be used, depending upon what you're trying to express and what you're trying to show. The 3-dimension stuff, we'll get into more detail when we start talking about orbitals and all that kind of stuff. And that's where we'll really be looking at the shapes of the molecules in addition to just what atoms are there. let's talk about ions for a moment. So an ion is simply an atom that loses or gains an electron. So if we think back to the moment, we said all these elements have a certain number of protons, and how do we know how many protons it has? Atomic number, right. So we said the atomic number is the number of protons something has. And then the atomic weight is the number of protons plus the neutrons, right? We also said that if you have a certain number of protons, because we're saying that it's neutral, then we have to have that same number of electrons, right? So can an element change its number of protons? Can carbon suddenly get more or less protons?
Changing the element.
Think back to what was one of Dalton's theories. He said that the elements don't change, right? Basically, is what he said. So we know that those protons don't change, right? So if we have the protons set, and we're saying a cation is something with a positive charge, that means it had to have lost an electron, right? Because the electrons are negatively charged. They balance out the protons, which are positively charged, to get that neutral atom. If we suddenly are positively charged and we couldn't have added or done anything to the protons, the only way to get that is to lose an electron. So for instance, maybe you have 6 protons and 6 electrons. If you take away one of those electrons, now you have 6 protons, 5 electrons, a net charge of +1. Anions are a similar thing, except there you're picking up an electron. So once again, if you had 6 protons and 6 electrons to begin with, you have a neutral atom. You pick up another electron, and now you have 7 electrons there. So it would be a net charge of -. So when we're talking about ions, we're talking about the atom either losing or gaining electrons. And then that changes the charge. If we look at this table here, these are ions that you should know. So this will be something you'll need to memorize. We see over in 1A, all of those are +1, 2A +2. We come over to 6A, 7A, we have -2 and -1 charge there. Remember we talked last time about periodicity. Here's an example of that. So we look in 1A. So maybe I remember that lithium is +1, that's the ion state it likes. And so, but I can't remember potassium for the life of me. Well, I know that these are all 1A elements. And so those, because they're 1A elements and that periodicity, they all show up as +1 charge. Same with the other 2A, 6A on the type things, is that you see that you start to see some of that periodicity showing up of where all the halogens in 7A, for instance, are going to be a -. Don't worry about hydrogen being negative. It's almost always plus. Okay, it's almost always a cation. It's an oddball thing when it's a minus. I'm not saying it doesn't happen, but it's not the norm. Focus on the H+1. So cations mean, what did we say? Are we picking up electrons or losing electrons? Losing, because we have a certain amount of positive charge. If we lose one of the negative charges that normally balances it, then suddenly we have a cation. Just the opposite for the anions. That's a negatively charged atom, and so then once you get that extra electron, then you have an overall negative charge. So these are some common cations and anions that we'll just briefly look at. The ones that are bolder, those would be the ones I would memorize first. You see over here, you see NH4+. We'll talk about that, the ammonium ion, in a bit. That's what's known as a polyatomic ion. And so it's not just elements. It can be you can have polyatomic ions as well, and we'll talk about that. Here's some more, some of the +2 and +3 ones, and then the names. We'll talk about naming convention as we go along as well. Here's some of the common anions: fluoride, chloride, bromide, the sulfide one. And then you see some polyatomics as well with the acetate, perchlorate, things like that, nitrate. So this is what we just mentioned about the table. Sometimes you have groups of atoms that will gain or lose electrons. So those are the polyatomic ions. Ammonium, NH4 plus is one. So if that is NH4 plus, did we gain an electron or lose an electron? We lose an electron, remember, because we have our positive charge, we have our neutral charge. The way to get that to be positive is to lose one of the negatives. Sulfate's a polyatomic anion, SO4 -2. So what happened in that case? Do we gain electrons, lose electrons? We would have gained 2 electrons, right? Because if we went from neutral to -2, the way we get there is to add 2 negatives to it. Okay, so we would have picked up 2 electrons there. So let's talk about ionic compounds now. We talked about the ions themselves, and now let's talk about ionic compounds. So in this example, we're talking about sodium chloride. And what you'll notice about ionic compounds is that usually they are the combination of a metal and a non-metal. The more traditional organic compounds, those tend to be just all non-metal compounds. But ionic compounds are usually a combination of these two. One thing that we mentioned was that what do metals like to do? Do they like to pick up electrons or lose electrons? They like to use electrons. We know that because the metals are usually positively charged. And if they're positively charged, if they're cations, that means they lost an electron. So we also call that donating electrons. The nonmetals, we saw a lot of those are negatively charged, so that means they like to pick up electrons. So it's kind of like a match made in heaven with the metals and nonmetals. You have one group of compounds that likes to give up electrons. You've got another group of compounds that likes to pick electrons up. So remember, we also said that opposites attract, right? So negative charge likes to hang out with positive charge. And so that's what we have going on here. We have those positively charged metal ions who like to donate electrons. We have those negatively charged nonmetals who like to pick up electrons. And so then they start associating with each other. What you see here in this kind of cluster of of green and bluish atoms is you see that inorganic compounds often form what they call crystals, and you have a crystal structure and all that. And so it becomes kind of a complex arrangement of all these atoms kind of stacked on top of each other. We'll go into a little more detail on that later in the semester. But because of that, these ionic compounds tend to be written in their empirical formula. So we don't worry about what that structure is and how many are stacked together when we write the symbol, the structure for that. We tend to just use the empirical formula to represent that. So sodium chloride is, as you can see there, is some lattice structure of molecules, but we don't write it all out. We just say NaCl. This is just a blown up version of that smaller table that we talked about. These are some ions, as I said before. You should go ahead and memorize what those charges are, because that'll come up later. When we write these formulas, how do we know how to write it? Well, if you look at the charge on them, so here we have magnesium and we have nitrogen. And so we know that mg is +2, and we know that n is -3. So we want the charge to balance, right? Because unless we're saying this is an ion, it's got to be neutral. So an easy way to do it is you look at what the charge of the anion is, in this case -3 on the nitrogen, and you make that the subscript on the magnesium, on the cation. You look at the charge on the magnesium, in this case it's +2, and you write that as the subscript on the nitrogen. And so then we know that this compound is Mg3N2. We can test to see if we got this right in terms of electrical neutrality by taking 3 times 2 for the magnesium, so that would give us +6, the total charge from those atoms, and then 2 times -3 for the nitrogen would tell us -6 for the nitrogen. So +6 minus 6 equals 0. So that tells us that we got it right. So one of the things we're going to talk about, and this will be our last slide, then we'll start the quiz. When we talk about naming compounds, this is known as nomenclature, and for chemistry, it's chemical nomenclature. And what we're going to learn is we're going to learn how to name ionic compounds, we're going to learn how to name acids, binary molecular compounds, and then a few of the simpler organic compounds, in particular alkanes and alcohols. So next class, we'll start going through this. Once again, this will be one of these things that the terminology in that is almost like learning a language, is you just kind of learn the definitions and learn what the molecules naming conventions are. So, okay, any questions on any of this stuff? Okay, then what I would like you to do is go ahead and log on to Canvas. And once you're logged in and you're ready to go, you can go ahead and start the quiz.
You don't want us to leave, right?
I'm sorry, what was that?
You don't want us to leave the chat, right?
You can.
Oh, okay, cool.